In section 3.3, we're going to solve quadratic equations and inequalities. But before that, we're going to do a quick review of complex numbers. Now, we're not going to go in depth into complex numbers and all their properties. We're just going to look at the basic idea of what an imaginary number is. So an imaginary number is this I, which we're going to define as equal to the square root of -1. So as we all know, the square root of a negative number does not exist. It's undefined, which is why we call the square root of -1 imaginary. Imagine squaring both sides of this equation and we'll get I squared is equal to -1. When we say complex number, what we're talking about is any number that can be written as a plus bi, and here a and b are real numbers. So that a is what we call the real part, and the b is what we call the imaginary part. So this is real, and this is imaginary, which makes sense because that bi is with the imaginary I. So since all complex numbers are made up of a real and an imaginary part, it actually includes, the set of complex numbers includes the real numbers. So all real numbers are complex numbers, but not all complex numbers are real numbers. So the set of complex numbers contains the real numbers, and it's actually larger than the real numbers. In example 1, we're going to write these complex numbers in a plus bi form. So whenever you end up with an answer that is complex, it should be written in a plus bi form. Now the square root of -9 is the same as saying the square root of 9 times the square root of -1. And we know the square root of 9 is 3, and we know that the square root of -1 is I, and I'm done. This is written in complex number form. Well, strictly speaking, there's no a value there, but if we simply put in 0 plus 3i, then we have this written as a plus bi, where a is 0 and b is 3. So this is an example of a complex number that's not a real number, because there's no real part. Let's try this again in part B. We have 7 minus the square root of -12. Again, we can rewrite this. So whenever you see the negative underneath the square root, you can kind of pull it out and make it be the I. So this would be the square root of 12 times I. Now this is not simplified though, because the square root of 12 is actually the square root of 4 times the square root of 3, and the square root of 4 is 2. We have 7 minus 2 square root of 3i. And this is now written in a plus bi form. So it doesn't have to be an addition in there. It could be a subtraction as well. And C is kind of weird. It's definitely not an a plus bi form, so I'm going to just multiply it out and see what happens. Well, when we multiply or FOIL this out, we'll get 5 times 5, so 25. We get a minus 5i plus 5i, and then a minus I squared. And then notice that the minus 5i plus 5i will cancel. That's just equal to 0. And I have 25 minus, well, I squared is -1. So this is 25 plus 1, or 26. And I'm done. So again, strictly speaking, it's not written in complex number form, but I can always change this to 26 plus 0i. So all real numbers can be written as complex numbers. And all real numbers are complex numbers. Something interesting happened in this particular multiplication. We got rid of the imaginary part. So this should take you back to rationalizing denominators where you had two terms and there were square roots, so we multiplied by conjugates. So conjugates mean same terms, but one's a plus and one's a minus, which is exactly what we have here. These are conjugates. So we have conjugates with square roots. We have conjugates when we have our imaginary number I. And when we multiply by conjugates, we get rid of I. Well, that's all I wanted to discuss in 3.1, just that review of complex numbers. Basically, I being the square root of -1. Because now we're going to use that when we solve quadratic equations. When we solve quadratic equations, because the highest exponent on our variable x is 2, what that tells us is we can have at most 2 solutions. And I know you guys are all familiar with our quadratic equation. We have seen it previously and graphed our quadratic equations in the last section. So now when we solve quadratic equations, we're going to look at first a special case. What happens if we don't have that x term? I'm going to go over a little bit of vocabulary here when we talk about quadratic equations. When we look at the squared term, that would be the ax squared. Again, this is what we call the squared term. So squared term. The bx is what we call the linear term. And the c at the end is our constant term. So quadratic, 3 terms, one is squared, one is linear, one is constant. Now, if we can take this quadratic equation and set it equal to 0, then we can find solutions, hopefully. And at most 2 solutions because the highest exponent is 2. The first case we're going to look at is if we don't have a linear term, so no x, just the x squared. So if we can get the x squared equal to a number, as in this property here, then the solutions are going to be x equal to plus or minus the square root of k. Why? Well, let's just look at x squared, something simple. X squared equal to 4. Clearly, the solutions are going to be both 2 and -2, which is the same as x equal to plus or minus the square root of 4. That would be x equal to plus or minus 2. So because of the square, we can put in both the negative and the positive and it'll work. And that's what we have to remember when we use the square root property is remember the plus minus. That's the one thing that people tend to forget. Example 2a, we have the squared term, we have the constant term, but we have no linear term. So we're going to try to isolate the x squared by first adding 48 to both sides to get x squared, or 2x squared, sorry, equal to 48. Then divide by 2 to get the x squared by itself. X squared is going to be equal to 24. So now we can use our square root property. If we square root both sides, this becomes x equal to plus or minus the square root of 24. And we have 2 real solutions. However, that solution is not simplified because there's a perfect square underneath the square root. 24 is 4 times 6. 4 is a perfect square. So the solution should be x equal to plus or minus 2 square root of 6. Now we can write it as x plus or minus 2 square root of 6, or we can write it in a set, and it's okay to leave the plus minus if you're writing the solutions. If you wanted to write it out as -2 square root of 6, comma, +2 square root of 6, that's fine too. They're all good. So again, notice we have 2 solutions, and they're actually real numbers. They don't have the imaginary I there. So I have 2 real solutions. Let's try this again. With b, we have x squared plus 16 is equal to 0. If I get the x squared by itself, I need to subtract 16 from both sides. And the pen's not working. To get a minus 16. Now that I got the square by itself, I can get x equal to plus or minus the square root of negative 16. And that's an imaginary number because of the negative underneath the square root. If I were to pull that out and write this as x equal to plus or minus, this would be the square root of 16i. But then the square root of 16 is just 4. So plus or minus 4i. And now in this case, we have two solutions, but they're not real solutions, they're complex solutions. And that's why we needed to review a little bit with complex numbers, because now we can actually find real solutions as well as complex or imaginary solutions. In C, I'm not sure if I can get it to look like x squared equal to a number, but I'm going to try. I'm going to isolate the squared term, the x minus 2 squared, and have that equal to 7. So we could still use this property. I'm ignoring what's in the parentheses. I see something squared equal to a number. I'm going to use the square root property, square root both sides, to get x minus 2, because the square root would cancel, is equal to plus minus the square root of 7. And then I'm going to add 2 to both sides to get x is equal to 2 plus or minus the square root of 7. And that's it. Those are real solutions. So I have 2 real solutions. Okay, now let's look at what happens if we actually have a linear term. The first thing we want to do is we want to look at what's called the zero property. And the zero property is very simple, but it's also very powerful. It says that if you have a product equal to 0, the only way that that can happen is if one or the other, or both, of the factors are 0. So the only way you can multiply and get 0 is if at least one of your factors is 0. And we're going to use that to solve quadratic equations. We're going to set them equal to 0, see if we can factor them, because these are factors, right? This is a product, and these are our factors. So we're going to see if we can factor, have it set equal to 0, and that'll allow us to break this down into 2 separate equations that we can solve. In part A, we have x squared minus 15x is equal to 0. Well, that's not factored, but if I factor out the common x, then I'll have x times x minus 15 is equal to 0. Now that it's factored, I have one factor is x, the other factor is x minus 15. I can set each one of those factors equal to 0 and solve separately. So x equal to 0, that's done. And I can even put in 0 into the original equation and see that it makes the equation true. I get 0 equal to 0. And the second one, I just add 15 to both sides to get x is equal to 15. Again, I could put in 15 into that equation, and it'll make the equation true. So I have 2 solutions here. I have 2 real solutions, and this would be the solution set. If I were to write it in a solution set, 0, 15. In part B, I have x squared minus 4x equal to negative 4. So this is not set equal to 0. Very first step is to get that equal to 0. So I could use the property, the 0 property. X squared minus 4x plus 4 is equal to 0. And now factor. It's going to factor into x minus 2x minus 2. So notice we have the exact same factors. So I only have to set one of them equal to 0 to get x equal to 2. And this is my only solution. So this is the case where you'll have one solution, and this happens to be one real solution. If I were to write that in a solution set, it would just simply be 2. And we could put 2 back in and we'll see that it makes the equation true. Let's go on to C. 2x squared minus 3x equal to 20. Again, not written in the correct form, so I have to set it equal to 0 by minusing 20 from both sides to get 2x squared minus 3x minus 20 equal to 0. And then I can factor this. If it does factor, it would be 2x and x, and it looks like it would be a plus 5 on the 2x and a minus 4 for the x. So 2x squared, I have a minus 8 plus 5 gives me the minus 3x and minus 20. Yep, that's how it factors. So now I can break this down into 2x plus 5. The idea is we want to just factor this so we can break it up into smaller little equations that are easy to solve, because it's very hard to solve if you leave it in the original form. Now if I minus 5 and divide by 2, I get x is equal to negative 5 over 2, and then x is equal to 4, which would be my two solutions. And these are two real numbered solutions. In a solution set, we have negative 5 halves, comma 4. Last example would be D, x squared plus 4x minus 1 equal to 0. Well, unfortunately, this is prime. I can't factor it and then break it down into the factors equal to 0. So since I can't really solve this by factoring, and I can't use the previous square root property because I have that 4x there, I have that linear term, what I'm going to do is look at the go-to way to solve equations, which would be our quadratic formula. The quadratic formula always works. Doesn't matter if you have one solution, two solutions, complex solutions, or real solution. Always works. And we all know this formula, that it's if you have the equation set equal to 0, so you can identify the correct A, B, and C, then the solutions are x equal to negative b plus or minus the square root of b squared minus 4ac over 2a. Now this b squared minus, hold on, don't want that. The b squared minus 4ac, that's what we call a discriminant. So if the discriminant, the b squared minus 4ac is 0, then you get one solution. Otherwise, you're going to have two solutions, and either they're both going to be real solutions or you're going to get two imaginary or complex solutions. Example 4 says solve. If the solution is complex, write it in the a plus bi form. Okay, so it is set equal to 0. I can identify, and this is from the previous example, that prime equation that I couldn't factor. So now I'm going to use the quadratic equation, noting that my a is 1, my b is 4, and my c is negative 1, which gives me the solution x equal to negative b, so negative 4 plus or minus the square root of b squared, so 16, minus 4. A times c is going to be negative 1, all over 2a. So remember, this fraction bar goes all the way across. It's not just underneath the square root. Oops, and here a is 1, so it's just all over 2. Sorry. Now I'm going to simplify that to get x equal to -4 plus or minus the square root of 16 plus 4. So this is going to be the square root of 20 over 2. And some people may want to reduce the -4 and the 2, but remember you can't do that because the numerator is not factored. The plus minus means that there's two terms. It's not factored. It's an addition subtraction problem. You can only cancel if you can cancel a 2 from every single term, including the square root of 20. But what I would do, though, is change this square root of 20 to, this is 4 times 5, right? And the square root of 4 is just 2, so this is going to be 2 times the square root of 5. Now, if you wanted to reduce by 2, you could reduce the -4, the 2 with the square root of 5, and the 2 in the denominator. So now you can cancel, but you have to do it from all three pieces. Or if you're unsure, go ahead and factor the numerator. You have a 2 in the denominator, so factor out a 2 from the, oops, I don't want a -2, I want a +2. Factor out the 2. You'll have -2 plus or minus the square root of 5 over 2. And hopefully now you could see that it's just the 2 cancels and you're left with the -2 plus or minus the square root of 5. A quadratic formula always works, but there are a lot of places where you could have some problem with computation, a lot of room for error. So I tend to use this as my last resort. Since I'm fairly quick at factoring, I prefer to see if something factors first. And then part B, we have a -x squared minus 3x equal to 4. Again, it's not in the correct form for me to identify the correct A, B, and C. So I would subtract the 4 from both sides and set it equal to 0. And this is correct, but I have a lot of negatives there, and I tend to not like working with negatives when I'm working with the quadratic formula. But just remember that you can multiply, this is an equation, you can multiply both sides by a -1. And when you multiply both sides by a -1, you get x squared plus 3x plus 4 equal to 0. Now that's a personal preference that I have, that I don't like a lot of negatives. But if you want to work with the negatives, that's fine. I tend to make more errors. Now I could see that my A value is 1, my B value is 3, and my C value is 4. In the quadratic formula, I'll have x equal to -b, so -3 plus or minus the square root of b squared, so it's going to be 9, minus 4. A times C is 4, all over 2a, so that's just 2. Underneath the square root, my discriminant is going to be 9 minus 16, so that would be a -7. And since it's a negative underneath the square root, that tells me that I'm going to have two complex solutions. So your discriminant, what's underneath the square root, can tell you how many solutions you're going to have. Again, if it's 0, you're only going to have one solution because that whole square root just goes away. If it's negative, you're going to have two complex solutions. If it's positive, you're going to have two real solutions. In this case, since it is complex, since I have that negative, I'm going to need to change this to x equal to, if I zoom out too much, my pen gets tiny. X equal to -3 plus or minus the square root of 7i over 2. But that's not in the a plus bi form. So the last thing I need to do is split this up into x equal to -3 over 2 plus or minus the square root of 7 over 2 I. That's in a plus or minus bi form. Okay, the last thing that we want to talk about is we want to look at inequalities. So the first thing I'm going to do is I'm going to look at this graph here. This is a graph of a quadratic equation or quadratic function. And there's some things that I can tell from this graph. In example 5, we're going to use this graph to find a bunch of stuff. And yes, I know I have another example 5. We're going to use the graph to find f of x equal to 0. So that says find x values so that y is equal to 0. You look on the graph, it looks like it would be -4 and +2. So that would be x is equal to -4, x is equal to +2, or as a solution set, it would be -4, 2. So those are the two x values that make this function equal to 0. Now, what x values in part B makes the function positive or greater than 0? So the function is positive or greater than 0 when it's above the x-axis. So that's saying the y values are greater than 0. So our y values are greater than 0, and now we have to state the x values that make the y values greater than 0. That would be for x values from, in set notation, -infinity to -4, parenthesis, because it's strictly greater than. And then again, greater than would be x value of 2. So I'm going to do a union to +infinity. Again, that's a parentheses. We don't include the 2 because that's when it's equal to 0, not greater than 0. In part C, it's asking us to find x values so that our function is negative. So those would be the x values that give us what's below. Sorry. The x-axis. So this is where our f of x or our y values are negative. And it looks like that would be x values from -4 to 2. It's going to be interval notation with parentheses because we do not include the -4 or the 2. What about D? What about f of x greater than or equal to 0? So that just means that you can include the -4 and the 2. Interval would be -infinity to -4 with a bracket, union, bracket 2 to infinity. So that says if I pick any x value within those intervals, my y value would be greater than or equal to 0. And now less than or equal to 0 would include the -4 and the 2. So -4 to 2 with brackets. What about the vertex? Well, if I look at the graph, it appears that the vertex is -1, 3. And that's a point, it's not an interval. What about the x-intercepts? Well, we already found those. The x-intercepts happen for the x values that make the function 0. So it's going to be the -4 and the +2 written as a point because the x-intercepts are points. Be -4, 0, 2, 0. So at those 2 points, we have our x-intercepts. Well, let's say that I want to figure out where functions are, quadratic functions are positive or negative or so on, and I don't have a graph. Let's say I just have an equation. So the steps that you want to take are to first solve the corresponding quadratic equation. So what that means is you're going to take the inequality, replace the inequality with an equal, and solve the equation like normal. And those solutions will be, as we saw on the graph above, those solutions are going to be where your function is equal to, always do that. going to be where your function is equal to 0. So those points correspond to the x-axis. So once you've found those points, then what that's going to do is it's going to break up the interval into intervals where the function will either be above the x-axis or below the x-axis. So again, we're finding these zeros so that we can break up our interval and then see where it's positive values and negative values. The second step is to identify the intervals determined by the solutions to the quadratic equation. So we're going to go over these steps in these examples. So it might just seem like a lot of words right now. And then once we have our intervals, we're going to test each interval to determine our solution set. So we're going to break up our number line. We're going to find test points within the intervals, test them in our inequality to see if it makes the inequality true or false. So let's go through those steps in example 6a. We have 2x squared plus 17x less than or equal to 9. So it says that we're supposed to replace the inequality with an equal sign to get 2x squared plus 17x equal to 9. And then we want to solve this quadratic equation to find where it's 0, our x-intercepts. First thing I want to do is I want to set this equal to 0 by subtracting 9 from both sides. Now I could use the quadratic formula, but this is factorable. It factors as 2x, x. I think it's going to be a 9 and a 1 plus x plus 9, 2x minus 1. So let's see, 2x squared plus 18 minus 1 gives me the plus 17. Yes, that's it. So now I would set each factor equal to 0 and solve to get x equal to 1/2 and x equal to negative 9. So we did part 1, we solved the quadratic equation, and we found these points that make our function equal to 0. We're going to take these points and we're going to break up a number line. So we're going to put 1/2 and negative 9 in the order that they would appear on a number line, and don't worry about correct spacing. We're just putting the two numbers. If we go back to our inequality, the original inequality, it was a less than or equal to. So that means that I can include negative 9 and 1/2 in my solution. So if I look at the intervals, I have an interval from negative infinity to negative 9, and I'm going to put a bracket. By the way, your book doesn't. They always just put parentheses. But since I know I can include negative 9, I'm going to write it with brackets. And then my next interval goes from negative 9 to 1/2, bracket. Last interval goes from 1/2 to positive infinity. Okay, so in between the negative 9 and the 1/2, I have these three intervals. And if I choose any x value from each one of those intervals, it'll either make my function or my inequality true or false. Okay, so let's see. We need a test point. Let's see, something less than negative 9, maybe negative 10 could be a test point. Between negative 9 and 1/2, I think 0 seems a reasonable number there. And then 1/2 to infinity, I would use 1. Okay, these are the test points that we're going to put into our inequality to see if it makes the original inequality before we messed with it. See if it makes it true or false. So if I put in negative 10 for x, I'll get 2 times 100 minus 170. Is that less than or equal to 9? So that is 30. Less than or equal to 9. That's false, which means I can't use any x values in that first interval. If I put any of those x values into my inequality, it'll make my inequality false. Well, I use 0 as a test point in this second interval from negative 9 to 1/2. If I put in 0, I get 0. This one's easy. less than or equal to 9. And 0 is less than or equal to 9. That means I could use anything in the interval -9 to 1/2, put any of those x values into the inequality and it will make it true. My last test point is 1 on my last interval. If I put 1, I get 2 plus 17 or 19, less than or equal to 9. That's false. So I can't use anything there. My solution set is going to be bracket -9, positive half with a bracket. So those are the x values that'll make my inequality true. Let's do one last example. We have 3x squared plus 12x greater than 0. First thing I want to do is find the corresponding quadratic equation. So 3x squared plus 12x equal to 0. Factor. I can factor out a 3x. That'll leave me with x plus 4 equal to 0, which gives me 3x equal to 0, x plus 4 equal to 0, and I have x equal to 0, x equal to -4. So these are the values that I'm going to break up my number line with. Again, you have to put them in the order that they would appear on the number line. The -4 comes first, and then the 0. This is strictly greater than, so I cannot include the -4 or the 0 in my solutions, if there are any. The interval would be -∞ to -4 parenthesis. The next interval that I'm going to test would be -4 to 0. And the last interval would be 0 to infinity. And I think some good test points would be a -5, from -4 to 0, maybe -1. From 0 to infinity, maybe 1. So those are the test points that I'm going to put into my original inequality. So remember, we're putting those test points into the original inequality. If I put in -5 in my calculator, let's see, what do I get? 15? Yeah, I get 15 greater than 0. That's true. So I can use that first interval. Let's see, next test point would be -1. If we put in -1, we have 3 minus 12. So -9 greater than 0 is false. So I can't use the middle interval. If I put in 1, I have 3 plus 12 or 15 greater than 0. That's true. So I can use that last interval. So my solutions are going to be -∞ to -4 union 0 to +∞. And that's it for this section.